Hello, 6988901.
I'm afraid my train's been cancelled again.
So how long do you think it will be? I'm just looking at the drawing now.
Quite a few things happening.
But I've got 2 bookings I've got to do now.
The telephone is so much a part of our daily lives that we take it for granted. Indeed, we seldom even think about it, unless we get a wrong number, or the person we want to get hold of urgently is out, or already engaged on another call. Yet have you ever thought of what goes on between us and the person we're calling, between our telephone and his or hers? What actually happens? How does the call get through?
Each telephone number's got its own wire.
Well, obviously, it must go into a computer terminal.
It goes through the wire, and when it gets to the person, the telephone rings.
Because when you dial a number, it sort of rings a bell in computer's mind. Through telegraph wires.
It goes through the pylons, the electric pylons, doesn't it?
You know, I've never really thought about it. I seem to take everything for granted.
It's signals, I think. Probably 1 is beep and 2 is beep beep.
I ain't got a clue. I'm a pipe fitter, not an electrical engineer.
It goes into the right box and comes out the right end.
Oh, God, no, I think that's too sophisticated for me.
This is a modern telephone switching centre, an international gateway, handling many thousands of our calls every hour, every minute even. Yet the telephone is only just over 100 years old. It's developed with amazing speed. But from the very moment that there were more than 2 telephones, telephone exchanges have been necessary to connect calls between them. And so telephone exchanges have had to develop too. And the story of how this has happened and of how they work is a fascinating, even a romantic one. Originally, all the wires from telephones led overground to the exchanges, high above the rooftops, and operators at that time connected all the calls. You simply asked for the number you wanted, and the wire from your telephone was connected to the wire leading to the telephone you wanted to call.
Yes, sir. What number did you require?
The plug put in by the operator was the connection between the 2 lines, between you and the person you were calling.
Just ringing for you, sir.
But the number of calls that could be connected manually was limited, and it was soon realized that some sort of automatic telephone exchange would be essential to keep pace with the rapid growth and popularity of the telephone.
Trying your number. Please be patient.
I asked for Oakley 58.
Yes, sir. I am still trying to get 58. It is still ringing, sir.
Well, don't keep making excuses.
But really, sir, that's no way to speak to me. We are in rather a rush today, you know.
Although quite a few attempts were made to develop automatic exchanges, the first really practical idea was put forward in America, in Kansas City, by an undertaker called Almon B. Stroucher. Stroucher was worried that he was losing business. As an undertaker, he thought that when people wanted to telephone him to arrange a funeral, his competitors bribed the operators to divert the calls to them instead, and so he lost business. He was determined to invent something that would work automatically. So Almon B. Stroucher came up with the first really practical way of connecting telephone calls automatically. And thanks to his ingenuity and foresight, many exchanges based on his switching principles are still in use throughout the world today, over 90 years later. But how does it work? How was the Kansas City undertaker able to devise a system that not only formed the basis of all early exchanges, but also established principles in automatic telephony that apply today? Well, what Stroucher had done was really to devise an automatic switch, a selector, that could make connections automatically. Each time we dial or push a button on our telephones, an arm moves on a shaft in the exchange and makes a connection with one of the contacts. It puts in a plug, if you like, just like the operators used to do in the early days. Now, our telephones have dials or buttons marked from 1 to 0. This is to say they send out 10 sets of signals. So if there were only 10 other telephones we ever wanted to call, then we could make the connection simply by using our own dials or buttons. But of course, there are very many more, and this is precisely what Stroucher realized, and what his remarkable invention allowed for. So if instead of connecting your telephone to 10 other telephones, you connect it to 10 more Strowger contacts, why, then you are connected effectively to 100 other telephones. From there, you can go on to as many further sets of Strowger contacts as necessary, and so on. The permutations are virtually limitless. Of course, Strowger's invention has been modified and refined over the years. But let's look at the system in operation. In this exchange, the sets of contacts in each of these banks of equipment can handle quite literally hundreds of thousands of our calls. And when you think that around 2,000 contacts are necessary for a local call and some 10,000 for a long-distance call, well, you can see just how many contacts there have to be. And it's all due to that remarkable undertaker from Kansas. But Strowger equipment can get worn or dirty, despite maintenance efforts. Something else was needed to cope with the ever-increasing demands. In the late 30s, engineers turned their attention to another kind of switching, something that promised to be more reliable than Strowger and quicker. Something called Crossbar. Crossbar is still an electromechanical form of switching, but the years of careful development work have ironed out most of the problems and transformed it into a practical system that is well named. When calls come into a crossbar exchange, small electromagnets are energized, causing the horizontal and vertical bars to operate in sequence. The magnets on the horizontal bars are called select magnets and make the bar move, like this. And these flexible select fingers prepare the contacts at that point to complete the circuit when the vertical bar operates. So when our call comes in, the bars move accordingly, operate the contacts, and connect us to the number we want. But to understand how Crossbar is able to fulfill its purpose as a reliable form of switching, we must go back to the beginning, because this link in our story, like so many successful inventions, grew from a very simple principle.
Won't be a moment, sir.
You remember that we've already said that operators made the connection by simply putting a plug into the appropriate socket. Well, let's look and see first just how the plug actually made the connection in some of the early switchboards. All the wires coming into the exchange were led to the switchboard and ended in these metal strips, vertical and horizontal, a sort of matrix. When the operator put in a plug, it simply connected two of these strips, a horizontal strip with a vertical strip. The plug itself actually made the connection. In essence, what the Crossbar Exchange did was to take and develop the same principle, the matrix system. It put a crossbar select finger and a set of contacts at each point where the lines intersect instead of a plug to make and break the connections as required. So, instead of having an operator to push a plug in and to pull it out when the call ended, the crossbars, or switches remember, did it automatically and very much faster. Virtually perfect contacts every time. Because these switches, or multi-switches, are so reliable, the system operates very efficiently. It has to. We've shown just a few working together. In exchanges like this, under actual operating conditions, there are many thousands of them that have to be ready to open and close the whole time the exchange is in operation. But nothing ever stands still. If it did, we'd all be running around covered in woad or something. No, developments go on all the time, often in parallel with one another. Nowadays, electronics help us in all sorts of ways. They've come to our aid in this part of the century, all right. Indeed, we're so accustomed to them now that it's becoming difficult to remember what it was like before. On the M1 this morning at junctions 16 and 32.
Letter to the Baltic Trading Exchange.
Telephone engineers were in at the very beginning of this revolution, with electronic exchanges. Why, the transistor was even invented in the Bell Telephone Laboratory. Telephone engineers were quick to realize the enormous advantages, the sheer capabilities of electronic equipment. As we've seen, Crossbar was and still is efficient, but electronics, especially new generation electronics, offer so much more. Because modern electronics have given us more efficient, smaller switches.
Now spell says. S. E. Said. Wrong. Try again. 8, 2, 8, 4 from 8, 7, 2, 8, 5, on, move. 8, 7.
Just think about what telephone engineers have been concerned with since Graham Bell started it all by inventing the telephone way back in 1876. First, the operator's plugs, then Strowger, then Crossbar, now electronics. Switches, all switches. Of course, electronics are nothing new to telephone engineers. The first electronic exchange was opened in 1962, and electronic switching was actually first invented back in 1919. But it was ahead of its time, and the right kind of equipment to make the invention practicable just didn't exist then. Nevertheless, some very eminent telephone engineers realized the enormous potential, and their work pioneered a new kind of switch that had a great many advantages over everything that had gone before, even Crossbar. And so in 1936, before the last war, this new kind of switch was invented, something called the reed relay, and it was a switch that was to prove much more reliable. It was called a reed relay because it depended upon two metal reeds that moved together when the outer coil was energized, and they were in a magnetic field, so making contact. The reed relay, a simple, reliable switch, something ideally suited to replace the Crossbar mechanical switching, especially when we remember the thousands of contacts necessary for our calls. But for this new switch to really fulfill its potential, it had to be coupled to a new kind of electronic control, an electronic exchange. And the development of solid-state components have now made it all possible, because reliability and efficiency aside, one of the main advantages of electronics to the telephone exchange is the sheer speed with which traffic can be handled, and the ever-increasing volume of calls to cope with makes this a very important point. And these modern electronic exchanges will now even diagnose their own faults. They actually pinpoint areas for engineers to investigate. But hold on a minute, that's not the whole story. Far from it. We've left something out, one of the most important bits. We've seen roughly how all the different kinds of switches work. Remember, the operator's plugs, the Strowger contacts, Crossbar, the reed relay, and so on. But how, when we make a call, is our line routed through all this equipment? How does it actually find its way to the right number? Well, when we lift the receiver and dial a number, the first thing that happens in the exchange to which our telephone is connected is that the signals from our telephone, our instructions if you like, go into something called a common control unit. And it's this control unit that works out all the routes available to our call and selects the best one. It's a kind of computer if you like, and it works just as fast. It has to. For you and I, this means that the moment the control system has set up one call, it can be released to be ready for the next one, and so on, minimizing delays. The control unit is in complete charge, and it guides our call through all the switching stages, perhaps even passing the call on to other exchanges and other control units if necessary, sometimes in other countries. But what about the future? We've already said that nothing stands still, and to prove it, just look at this. Continuing developments in electronics have led to miniaturized circuits, tiny integrated circuits like this, so small they can slip easily through the eye of a needle, and yet they contain many thousand components. But even that piece of man's ingenuity has been superseded. To see one of the future ways that telephone exchanges will be developing, we're going to have to look through a microscope, a very powerful electron microscope, to magnify what we're looking at many thousand times, because the switches of the future are so minute. This is a silicon chip, a tiny piece of silicon made up in layers and specially treated. It can do wonderful things like passing impulses through its tiny circuits. A chip this size actually contains around 10,000 switches. And in telephone exchanges, the chip is replacing the reed relay, giving us a new generation of exchanges known as System X. These new exchanges will route our calls at almost the speed of light, around 186,000 miles per second. And they'll provide a range of facilities hitherto unobtainable, because this is the future of our 6,300 telephone exchanges. A whole new generation of equipment and ideas that are going to revolutionize the way we use our telephones and the service we get from them.
Diversion on no reply service. Dial the telephone number to which you want your calls diverted, followed by square. Diversion on no reply is now in operation. Incoming calls will be diverted to telephone number 54.
We shall be able to tell the automatic exchange if we don't want to be disturbed. We shall be able to program alarm calls, or hold one call on the line while we take another if we want to. And this is only the tip of the iceberg. Exchanges like this are starting a whole new generation of uses for the telephone. It's all made possible by System X, and the latest in new circuitry and new switching techniques. But there are many things on offer already from our telephone system. We can carry tiny radio pages around in our pockets to alert us when we're wanted on the telephone. The telephone system can already carry the printed word. And it can also transmit drawings and pictures along telephone lines, all with the speed of light. Television cables already carry many of the TV pictures we see over parts of this country and across the world. And now conferences between businessmen in different cities can be arranged by contravision.
Yes, very involved, very high peaks.
Above 25 on the chart, you've got some very thin trend lines. Is there any significance between the trend line and the very base line?
Yes, well, we think...
Contravision is a form of closed-circuit TV developed by British Telecom. By using both cables and microwave links, these carry picture and sound and enable people to talk together quite freely and easily in different cities.
You'll find that as they come near the end of the...
Enable them to talk together and to see one another, although they may be very many miles apart.
Taken away.
Did you realize that callers in African countries often have their calls routed through here, routed through this switching centre in London, and then back again to Africa? Transatlantic calls are also often flashed across to this switching centre and then back again across the Atlantic, all the way to South America perhaps, again at the speed of light itself. Yes, we've come a long, long way since the first operator put in the first plug in the first telephone exchange.
29. Yes, sir, just one moment, please.
For which country, please?
Of course, we shall always need operators in any telephone system. Operators to handle emergencies, to help with problems, and to provide a personal service. But the increase in telephone traffic is so enormous that it would now require the entire population of London to act as operators just to connect all the calls made daily.
Is there no number on the box? Yes, what number? Right, just one moment.
The world telephone network has grown to a giant. More than 400 million subscribers who can simply pick up a telephone, dial a few numbers, and be connected within a few seconds to any of the others. That's communication for you. In just over 100 years, the telecommunication network has become the largest machine man has ever built. And it's still growing, still adding to the things it can do for us. What will it do in the next 100 years? Who knows? We can only guess at some of the things that will be done by telephone exchanges as yet unbuilt. Only one thing is certain. The telephone system will always serve us because it is always dependent upon the people who use it. and it always will.
The electricity goes through the wires, and then when it gets to the person, it goes off.